Hi, and welcome to our final discussion in our acid-base unit, lesson 4a, which is going to look at acid-base equilibria. Of course, the presence of a letter after the number in our lesson sequence means that this is very much an honors-only lesson. This chart is showing you 6 strong acids and 6 strong bases. These are going to be probably some of the most common acids and bases that are used in the chemistry lab, for reasons that we'll discuss in a second. Let's go ahead and take a look and see how this works. One way to describe acids and bases is in talking about their strength. What we mean by this is how completely the acid or the base ionizes in water. We're not referring to its concentration. Strong acids and bases ionize completely, functionally 100%. That's what makes these strong acids and strong bases strong. If we put them in water, they will totally ionize. Most acids and bases, however, are not strong. Most acids and bases will not completely ionize when you put them in water before you reach an equilibrium between the dissociated and non-dissociated versions of the acid or the base. Water is a classic example of this. It does not ionize completely in solution. All of the water molecules do not exist as hydroxide ions or hydronium ions. In fact, only 1 in every 10 million water molecules at 298 degrees Kelvin exists as ions, and it only lasts as an ion for 1 picosecond or 1 trillionth of a second before it reverses back into its non-ionized form. Because of this, we need to have a way of describing acid or base equilibrium. For acids, we're going to use Ka, which is the acid-ionization constant. It's just the equilibrium constant for acid dissociation. If you need to go back and review equilibrium constants, I would definitely encourage you to go back to Unit 10 and check it out before we move on. Ka values are calculated a little bit differently than Keq values. For any reaction between an acid and water that produces a hydronium ion and the anion of the acid that reaches equilibrium, Ka is equal to the product of the hydronium ion concentration times the concentration of the anions divided by the concentration of the undissociated acid. There are no coefficients shown in this example, but if they were present, they would work the same way that they worked in terms of calculating Keq. The equation for Ka is given to you on your honors reference tables, and you should be able to use it, but the bottom line is that the larger the Ka value, the more ionized the acid is at equilibrium. For bases, we talk about Kb, or the base-ionization constant. This is the equilibrium constant for base dissociation. It works exactly the same way it did for acids, except the base becomes a hydroxide ion, and the cation of the base absorbs a proton from the water molecule. So Kb is equal to the product of the concentration of Hb plus times OH minus divided by the concentration of the undissociated base. Kb is not given to you, and for reasons that we'll discuss in a second, you can always use Ka values to help inform your understanding of Kb, but you won't be asked to calculate it. We can use Ka and Kb to do some interesting things. For any substance that can act as an acid or a base, Ka times Kb has to equal Kw, the ionization constant for water. This diagram shows you the members of a conjugate acid-base pair for a bunch of different substances, and you can see that in each case, Ka times Kb equals Kw. For stronger acids, Ka is going to be functionally 1.0, which means Kb is going to be 10 to the negative 14, and for stronger bases, Kb is going to be 1.0, which means that Ka has to be 10 to the negative 14. In between is where we see things that are not really strong acids or bases, and in each case, Ka times Kb equals Kw. It's probably natural to wonder, why is this useful? You're provided with a series of Ka values on Honors Reference Table C, which is the relative strengths of acids in aqueous solution at 1 atmosphere and 298 degrees Kelvin. From this, because Ka times Kb equals Kw, you can always calculate Kb values off of it. You can also use this to predict the behavior of different substances when they're mixed together in a solution, in terms of whether they'll act as a Bronsted-Lowry acid or a Bronsted-Lowry base. If we look at water and ammonia producing a hydroxide ion and an ammonium ion, we can see that the Ka value for water is 10 to the negative 14, and the Ka value for NH3 or ammonia is very small. That's how it's listed on Honors Reference Table C. Similarly, the Ka value for the hydroxide ion is 10 to the negative 36, and the Ka value for the ammonium ion is 10 to the negative 10. Using this, we can determine that water is going to act as an acid when it's combined with ammonia, and ammonia is going to act as a base, because water's Ka value is larger than ammonia's Ka value. Similarly, we can determine that the hydroxide ion is going to act as a base, and the ammonium ion is going to act as an acid, because the Ka value of the ammonium ion is larger than the Ka value of the hydroxide ion. Does this make sense? If not, take a moment and write down any questions that you have before we wrap up. Thanks so much for watching our discussion of acid and base strength. Make sure you can do the following things here at the end. Make sure that you can use Ka to determine the strength of an acid or a base. Make sure that you can solve for Ka and make sure that you can use it to predict if a substance will act as a Bronsted-Lowry acid or a Bronsted-Lowry base in an acid-base equilibrium. If you can do all these things, you're doing great. If not, that's okay too. Take a moment to write down any questions that you have. You can always leave them for me in the comments below the video, and you can always get in touch with me. Thanks again for watching. I really appreciate it. Have a great day.